Hello, my name is Yannic, and today I will present our paper Batched Vertex Cover Reconfiguration. This is joint work with Keren, Censor-Hillel, Shahar, Romem-Peled, and Tigran, Tonoyan. We're all from the Technion. So, as said, this paper is about vertex cover reconfiguration. So, how to get from one vertex cover to another vertex cover. So, let's start. So let's start with some motivation and some gentle introduction into the topic. So consider a computer network, and what you want to do here for security reasons, you for example, want to monitor all links. So you place some agents in some of the vertices, some of the computers, such that every adjacent link is monitored. But now after some time, maintenance is needed. So what you will want to do is you will change the monitoring machines here and select different ones. And what you of course want to do is, even during the change, you want to always monitor all of the edges. And what we want to do here is we want to study the smooth transition from one set of monitoring machines to another one. And formally, the set of monitoring machines is nothing but a vertex cover. So a subset of the vertices that touch all of the edges. So the problem that we've just seen is formally known as the vertex cover reconfiguration problem. So here you're given an initial vertex cover, denoted as alpha, the blue vertices, and the final vertex cover here denoted as beta, the green vertices. Then the goal is to compute a reconfiguration schedule. That is a sequence of vertex covers, where the first vertex cover is alpha and the last vertex cover is beta. And two consecutive vertex covers are only allowed to be changed to differ by a single vertex. So in this example here, you could, for example, first add this green vertex here to the vertex cover. Then we can remove two of these blue vertices up here from the cover because these edges are covered by the green vertex. And now we can add another of the green vertices, remove more, and so on, until we've reached the vertex cover beta. The length of such a reconfiguration schedule is one of the parameters of interest, but throughout this talk, we will only consider so-called monotone schedules, where you can only change each vertex once. So it can only just leave the vertex cover once or join the vertex cover once. And if you then look at sequential vertex cover reconfiguration, the length is always just the symmetric difference of the initial and the final vertex cover. And the cost, as usual with vertex cover, you want to get vertex covers of small size, is the maximum intermediate vertex cover. So what you want to achieve here normally is that your intermediate vertex covers throughout the reconfiguration process are also small. And then one thing that has been classically studied is the vertex cover reconfiguration decision problem. So you're given a graph and some parameter k, as well as two vertex covers, alpha and beta. So they're given as part of the input. Is there a schedule with cost at most k? And it's known that this is a difficult problem. It's p-space complete, and even on planar graphs with degree at most 3, and even on bipartite graphs. But there are examples where the problem is actually in P, on, for example, so-called even whole-free graphs. So in this paper, we want to provide a new angle to this vertex cover reconfiguration problem and reconfigure faster. Because if you're in such a large network, then you can maybe add two vertices to the vertex cover at the same time, if they're not in conflict, or also remove some, or at the same time if there's no conflict in these actions. So what we will look at in this paper is batch reconfiguration, where you're allowed to change more than one vertex at a time. So let's see, how do we need to change the definition of a reconfiguration schedule? Before, what we had is here that we are only allowed to change one vertex at a time. Now we change this that we are allowed to change an unbounded number of vertices. what can happen if you just try to do this? Well, one bad idea is to just in one change, just without any further restrictions, you can just immediately go from the initial vertex cover alpha to beta, just in one batch, and you're there and you're done. Why is this nothing that we want to do? Well, if we execute all these changes in one batch, well, in this batch we have some agents which leave the vertex cover, some nodes which leave the vertex cover, others which join the vertex cover, and they're all in the same batch. But if you look at the system where you want to monitor some things, see that it's actually an asynchronous implementation of these changes, and we cannot assume that all of them happen exactly at the same time, even so they are in some batch. So what we assume here is that we don't have a control on the order inside a batch. We don't know in which order these changes to the current vertex cover will be executed. But still, what we want to have is feasibility, validity. So we still want at each point that every edge is monitored by at least one of its endpoints. And it's clear that here, if we put both endpoints here into one batch, adding this green vertex and removing this blue one here, then it might be that the removal of the blue vertex is executed first, and then this edge is not monitored anymore. So we need further restrictions to prevent this, so we really do have a monitoring of all edges at all time. So one can easily circumvent that by, okay, one can say, I just start with my initial vertex cover, then I add all the vertices which are in the green vertex cover, and then I remove the ones from the blue vertex cover. So I just need 2 steps here. I have a lot of parallelism, it's very fast, but the problem here really is, okay, in this previous step, in this intermediate step here, we actually have a vertex cover which is very large, which is almost all of the vertices. And this is also nothing that we want. It's too expensive. We want small intermediate solutions. And we also want these small intermediate solutions regardless of which order inside a batch the changes are actually applied. So what's our definition of a batch reconfiguration schedule to obtain both of these changes and to have both of these? So a batch reconfiguration schedule, and now it's actually complete, not incomplete. So reconfiguration schedule, where after each batch, we have to output the vertex cover. We can change as many vertices at a time as we want, not just one. But we need that even in an adversarial sequential execution order within a batch, each edge is covered at all times. This can, for example, be achieved if one always just reconfigures in one batch nodes which form an independent set. This is an equivalent statement. And for the cost, we simply charge the schedule for the cost that can happen and appear in a worst case order of applying the changes within a batch. So if you look at the change from CI to CI plus 1, so changes from one batch, it might be that the order is such that first all additions are done and only afterwards the removals. So it might be that the worst case bound on the size is actually achieved, which just is the union of 2 consecutive vertex covers. So this is the definition of a batch reconfiguration schedule. And this is the object that we mostly study in this paper. So since this is something which has not been studied before, we have quite a large number of results here, and we have some centralized results, which are on the existential side. We show that certain schedules exist. also some polynomial time algorithms, and we have distributed results where we present distributed algorithms to compute such schedules. I won't be able to present all our results in this slide, but let me give you a short overview of what kind of results we have. So let's first start with what we've seen. We've seen that we introduced this new concept of batched schedules. And then we also have a generic method to create such batch schedules if you have sequential schedules. We will look at this in detail later, but the bottom line here is if you have order of 1/epsilon batch schedules, then you just use a 1 + epsilon factor in the optimal cost. And this is actually optimal. Then we have several new sequential schedules for various graph classes, such as planar graphs, bounded diversity graphs. And also we unify some proofs for already known sequential schedules for different graph classes. And we provide some existential lower bounds. And we also provide some very short schedules for planar and bounded diversity graphs, which really just have 4 batches. This is a quick overview of centralized results. Then we also have distributed results where we have distributed algorithms, later tell you what these are, to compute such batch schedules. So we complement these results with lower bounds, weighted and unweighted lower bounds. And we also present distributed algorithms using different techniques to get schedules with different trade-offs. So since these are quite a large number of results, I will only focus on 2 of these results, which are easiest to present here in this short talk. So we'll first start with this schedule compression here, which takes a sequential reconfiguration schedule of a certain length and compresses it. Basically, what it does, it creates a new schedule which just has a small number of batches without increasing the cost a lot. So sequential to batch. And now let me first start with what do I mean by only some 1 + epsilon factor increase in the cost. This is more or less what you know from classic approximation algorithms. We say a schedule is an eta c approximation if its cost is at most eta times m plus c, where m is, and this is different from how approximations are usually defined, it's not the optimal, the cost of an optimal schedule, because we don't know what it is, and sometimes it's even incomplete to compute, but actually m is just a lower bound on the optimal schedule. Set this m to the maximum of the initial and the final vertex cover, because any schedule has to start with alpha and with beta. So the cost of any schedule will always be at least this maximum. And you can define these approximation costs for sequential schedules and for batch schedules. And our theorem says that if you have a monotone sequential schedule, which achieves an approximation, then we can create a monotone batch schedule, which just 1/epsilon batches, so order of 1/epsilon batches. And we only use 1 in the additive factor here and an epsilon in the multiplicative factor of the approximation. Let's go through the core ideas of this proof. So what we're given here is a sequential reconfiguration schedule. Now we enumerate the elements in the schedule. So all the elements of beta that we add, we enumerate them as B1, B2, B3, B4, in the order how they appear in the schedule. And we do the same for the elements of alpha that we remove from the vertex cover in the order how they appear in the schedule. Note that the numbers are just within beta and within alpha. This is different for the next definition, which is a time, or the slot, in the schedule which a node appears. So for example, the time when A1 appears in the schedule is 4 because it's a 4th element in the schedule, while the time of B4 is 6, it's a 6th element in the schedule. And with these definitions, we can come to one observation. The observation is that the time of BI plus C is larger than the time of AI. Sounds pretty technical, but what does this mean? We are here in this situation. Up here, we basically show, well, there might be some vertices in between here, but we show that AI comes in the stream, or not in the stream, in the schedule before BI plus C. And this basically just means that if we've added B1 until BI plus C, we can safely remove A1 to AI without getting any problems with uncovered and not monitored edges, because the same happens in the original schedule. This is all what this means. So let's look at a proof of the statement. This is just by contradiction. If this was not true, then after adding B1 until BI plus C, we only would have removed A1 to AI minus 1. So that would mean at this point in time here, after we've added this vertex here, the size of the vertex cover would just be the initial vertex cover plus the number of vertices that we've added minus I minus 1. And this is a contradiction to the approximation guarantee that the schedule provides us. So with this observation, we can now compress the schedule simply as follows. We set the parameter k, which determines how many batches we will get in the end. And then we give the vertices in beta that we want to add a head start of C vertices. And afterwards, we always just add k vertices of beta, remove k vertices of alpha, add the next k vertices in the original schedule from beta, and remove the next k vertices from alpha. And this observation shows that in this case, we never get a problem with validity. All edges are always covered at all times. So this is the schedule that we then get in the end. To summarize the schedule, you have this compressed schedule here. Yeah, always have all edges covered, even if these batches are executed in any sequential adversarial order, where, I mean, within the batch, it's executed in an adversarial order. The schedule lengths, well, each of these batches here has size at least k, so we will just have the number, the original schedule divided by k as the length. And the cost, well, the maximum cost is achieved here at this point in time. After we give this head start and we add another k vertices, that's where we have the maximum cost. Because afterwards, we always just remove k vertices, add k vertices, remove k vertices, add k vertices, and so on. So here's where we have the maximum cost. And what is the cost here? It's the initial vertex cover plus c plus k vertices. This is how many we added. And just do the math and you'll end up with the claimed approximation factor. And this has several implications for the existence of batch schedules. For example, for cactus graphs. Cactus graphs are graphs where each edge is in at most one cycle. And one knows from previous work that these always have 1,2 approximation schedules. And now one can just use the compression scheme to see that cactus graphs have reconfiguration schedules with order of 1 over epsilon batches and an approximation vector of 1 plus epsilon, comma 3. And actually, these proofs don't need that the whole graph G is a cactus graph, but only that the symmetric difference of these two vertex covers is the cactus graphs. And this is why this results actually hold for larger classes of graphs. And we have more such existential results also for planar graphs and bounded diversity graphs. So look into the paper for the additional results that I don't want to mention here now. Instead, now I want to talk a bit about our actual motivation, the reason why we looked at this problem. And this comes from distributed computing. Because in the distributed setting, this is where it really makes sense that you don't reconfigure nodes one by one sequentially. Consider some very large network there where communication from one end of the network to the other end of the network takes a very long time. Here, it doesn't make sense that these nodes coordinate and wait for each other. We want to actually achieve a lot of parallelism and even deal with parts of the graphs more or less independently. So let's look at the model that we consider here in the distributed setting. This is a classic message passing model, the so-called local model, where we take such a communication network, you could just see it here, communication network, and we abstract it as a graph. Everyone has a unique ID. And now these nodes in the graph, they can communicate with each other. And this communication happens in discrete synchronous rounds. So in one round, the vertex can perform some local computations and exchange messages with all of its neighbors. And everyone here acts at the same time. And we do not charge the vertices for the local computations. And also the message size is unbounded. So the term complexity is only the number of synchronous rounds until we've solved the problem at hand. So one thing to point out here is that all nodes act simultaneously here and all nodes start in the same round 0. So this model abstracts away a lot of things, but it's one of the classic models in that area. So what does this model now mean for the vertex cover reconfiguration problem? So the setting that we have in the vertex cover reconfiguration problem is that one of these networks in the graph here, one of these nodes, computers in the graph, doesn't know what the graph looks like. All that they know at the start of the computation is their own ID, and they know whether they are in the initial vertex cover alpha and whether they are in the vertex cover beta. That's their knowledge. And then they can talk to other vertices, learn a bit more about the network, learn the status in alpha and beta of the other nodes. At some point, they've seen information from some part of the network, some part they haven't seen, and still what they need to output at the end is the schedule. And this output, the schedule, means they should output their own part of the solution in the schedule. So they should know in which of the CIs are they contained. And what we asked now, can we in this distributed model here compute such schedules efficiently? Let me first say that we're not the first people to study reconfiguration in this model. It has actually been done for graph coloring, where you're given two different vertex colorings. So here, every node initially knows their color, that they have a green color at the start and should have a red color at the end, for example. And you want to always keep changing vertices, and you can change vertices in parallel. Again, you can only change independent sets here in this model. And you should use as few additional colors as possible. So you have some additional colors to use here. And in each intermediate step, you want to have a feasible graph coloring. And it has also been studied for independent sets itself, where you have an initial independent set, need to go to some other independent set. And here one cannot maintain the property to always have a proper maximal independent set in the intermediate configurations, but one can only keep that one has an independent set, but one has to loosen the condition on maximal to actually compute schedules and to even have it solve these problems. But let's now go back to our problem, vertex cover reconfiguration in the local model. Now, what I present now is our core tool that we use to compute these, which is a small diameter, small separator decomposition. What you want to do, because you've already seen that a node in this model can only learn some information from close by and coordinate with vertices that are close by, is that you want to group nearby vertices together. And then you actually want to deal with these parts at the same time to have a lot of parallelism, and they should work in parallel without any interference. And this is why we come up with such a decomposition, which decomposes the graph in small clusters, with small diameter, because in small diameter, you can always compute things efficiently in the local model. And the clusters are made independent by inserting separators in between, separating nodes in between these clusters. And the object that we obtain then is what we call a small separator decomposition. And in fact, it's a decomposition of the graph into clusters and a separator set, such that each cluster has a small diameter and that the separator set has few vertices. Additionally, and this basically describes that the set is a separator set, each edge of the graph is either completely contained in a cluster, look, this one edge here, for example, or has one of its endpoints at this edge here in the separator set. So you cannot have an edge from one cluster to another one. So what we then show is that if you're given such a decomposition, and you know that there exists a good schedule for each cluster, this is the condition here on the left-hand side. This is actually a weak condition that it exists. Then we can compute a good batch schedule for the whole graph to reconfigure from alpha to beta for the whole graph. And we just lose a bit in the parameters in terms of the size of the separator and the number of clusters. So let's try to prove this result. So let's look at a first attempt on how to solve it. So let's actually look at vertex cover, and here you can already see that the approximation will be violated. But here we're given some vertex cover. We have some vertices which are in beta, some which are in alpha, and some which are in both. So the first attempt would be to really separate these clusters, which means this is our initial vertex cover alpha. And now we would add all green vertices in the separating set to the vertex cover. So this would just be in the first step, we would add this vertex here. So now you can see really there are no edges leaving a cluster that you need to take care of. And really all these clusters are independent. We can just look at the clusters independently, and we will never have a problem with feasibility that we forget to monitor any of the edges, because all edges leaving the clusters will be covered at all times. So now we wish to just reconfigure both of these clusters at the same time. But now what happens if you reconfigure the left-hand side cluster here? Well, in this cluster, we have no chance other than we need to add the green vertex here. What do we need to do in this cluster? We have no chance but to just add all of the green vertices here. So in the next step, what happens here is that actually all the vertices here are in our intermediate vertex cover. Then in the next step, we finish the reconfiguration inside the cluster. So we're still in step 2 here by removing all these blue vertices here. Now we're in a good situation again. And now we would remove all the blue vertices, which are not green from S in this place. There's none. And what we've seen now in this step 2, we at some point had a lot of vertices inside the cluster. And this violates the approximation guarantee that we're given by our theorem. So one actually needs to do something a bit smarter. What one needs to do here, you first reconfigure all clusters in which alpha has more nodes than beta nodes. And only afterwards, you reconfigure the clusters in which beta has more nodes than alpha nodes. So in this particular example here, we again first add the separating node here. And now would first reconfigure the left-hand side cluster and not do anything at the right-hand side cluster in this step. So the schedule really would say here, okay, first we're done with this cluster. Now we've already freed a lot of our capacity, and only now the schedule would be to reconfigure the right-hand side cluster by adding the green vertices and then removing the red vertices. So what I've been presenting here are the schedules and not the actual computation. The actual computation here in the local model is trivial because of the small diameter of the clusters. So let me not go into the detailed computation of why we actually achieved this approximation factor, but for those that are interested, I'll put the calculations on the slides and you can pause the video and look at them. Instead, let me now just emphasize that this small separator decomposition comes with three important parameters that affect our runtime on how long does it take us to compute the schedule, but also the quality of the schedule. So this X, the size of the separating set, goes into the quality of the schedule. How good of an approximation is it? The number of clusters goes into the quality of our approximation, and the diameter of the cluster goes into the runtime. So basically, the runtime of our local algorithm will be if we take t rounds to compute the decomposition, and our diameter is d, then the whole algorithm in the local model takes t plus d rounds. So two of the parameters are concerned with the quality and the diameter of the clusters with the runtime to compute the schedule. What can we obtain now? For computing such decompositions, we can basically get all these parameters small. We can compute these decompositions very efficiently if the symmetric difference of the vertex covers is a cactus graph, and this is true for quite a large class of graphs. Then in log star n over epsilon rounds, we can compute the d comma x separator decomposition, where x is just an epsilon fraction of the symmetric difference. The number of clusters is just epsilon times the size of the vertex covers. And the diameter is also just 1 over epsilon. So all these parameters are actually pretty good. And as a corollary, by plugging in really all the things that we've seen about existential results, then the batch compression, computing such separator decompositions, then using them for computing reconfiguring tells us that we can very efficiently in log star n over epsilon rounds compute in a distributed setting schedules with order of 1 over epsilon batches, which are very close to the best thing that you can achieve. They just have a 1 plus epsilon comma 3 approximation guarantee. Just say that the algorithm for this cluster merging is inspired by GHS and GKP. So these are distributed algorithms for computing MSTs. So basically what we do here is we initially make every vertex their own cluster, and then we keep merging clusters to grow larger and larger clusters. And what is the main reason why we get a small separator set? Because then these clusters are not separated. Well, what we use here is that cactus graphs have only 1.5 times the number of nodes edges. And they're actually also closed undertaking minors. So if you look at the cluster graph, where you take each cluster and contract it to a single vertex, then this cluster graph will also have few edges. And then from each of these edges of the cluster graph, we will remove one of the vertices. So actually the separator set will be roughly the number of clusters that we get here. So we basically grow the clusters until we have few clusters, then we create the separator set. But this is just a high level idea because this might actually create new clusters, and a few additional tricks are needed if you're interested in this decomposition, because it might actually be helpful for different problems as well. Please have a look at the paper. So that's it. Thank you very much. And for open problems, I didn't put anything on the slide. Let me just tell you all the things I've been told you hold for monotone schedules, and it's a big open problem and very unclear what happens if the schedules are not monotone anymore. Thank you very much.